Hello. So in this final video of this chapter, we will still be in double replacement or double displacement reactions, and this time really going through the steps in determining which of the products is soluble or insoluble and writing net ionic equations, and also looking at the other types of reactions that can be double replacement reactions, neutralization, and gas forming reactions. So again, this is another diagram of what a double replacement reaction looks like when it forms a precipitate. We can see the reactants are aqueous over here, and which means they're dissolved and dissociated. Then they mix together to form the solid lead iodide, and here's the aqueous potassium nitrate still floating around. So how do we determine which one of those two ionic compounds, if any, are soluble or insoluble? Well, this is the chart from our textbook that gives us the solubility rules, and I like this one in particular because it really highlights for us the ones that are most important. So what's really important, you never have to memorize these. These are absolutely going to be on the test for you to use. But the ones that have very few exceptions are the ones that are really important to know. And that is the alkali metals and ammonia. So if you look at the periodic table, what are the alkali metals? Lithium, sodium, potassium, rubidium, cesium. All those guys, no matter what they are bonded with, will always be soluble. The other always that is important to know is anything with ammonium and also anything with nitrate. So sodium nitrate, lithium nitrate, but also lead nitrate, copper nitrate, anything with nitrate is soluble. After that, there's lots of exceptions and sometimes rules. So that's why I like this, and this is the version that you will have on your tests. It's organized by the negative ion, so that's a little different because the negative ion always comes second in the formula of the compound. But what you do is you look up the negative ion, and then you look and see, well, what is that matched with? Again, the all rules are still here. So all the alkali metals, and I listed them there, the ammonium ion, everything with ammonium is always soluble, and nitrate is always soluble. Those would be the ones that I try to remember. Everything else you can look up. This is also really good because on the test, you're going to need to know those polyatomic ions really well. And theoretically, you should have them all memorized, but in reality, you probably have forgotten some of them. So here you can see that a lot of the polyatomic ions are listed as well. Okay, so let's do an entire problem from start to finish. So here we have lead nitrate, lead 2 nitrate, and sodium sulfate. And so what I want us to do is we're going to figure out the products, then balance it, figure out which one is solid or aqueous, write the complete ionic equation, and then the net ionic equation. These take a little bit of time. So the first thing we need to do is figure out what the products are. And that's taking the positive of one and matching it up with the negative of the other and making sure we crisscross the charges here. So the first one is going to be lead 2 plus and sulfate 2 minus. So that's going to be PbSO4. And then the other product is NaNO3. Okay. Now second, balance it. All I need to do is put a 2 in front of the NaO3, then it's balanced. Now I go back to the solubility rules and look and see which one of these is solid and which one of these is aqueous. If you remember the always rules, sodium compounds are always soluble and nitrate compounds are always soluble. So right off the bat, I see that this is aqueous. Let's look at lead sulfate. So I find the sulfate rule. The sulfate rule is number 6. And it looks like when it's matched with lead, it is not soluble. That means solid. So this is my solid. So now I have the complete balanced chemical equation. The next one is the complete ionic equation. And remember, this is anything that's aqueous, we actually write out as the aqueous ions. This takes a little bit of time, but this helps us to get the net ionic equation. Okay, so now we, first of all, make sure that you have the right number of these ions. When it says 2NaNO3, that means 2Na plus and 2NO3 minus. Same thing down here. If it's Na2SO4, when it separates into 2 sodium ions. So this is the complete ionic equation, and from this we can see pretty clearly that, at the beginning of the reaction there's nitrate ions floating around, and at the end of the reaction there's still nitrate ions floating around. Those are not participating in the solution. Same thing with the sodium ions. So we call those the spectator ions. And the net ionic equation is the equation with the spectator ions crossed off, just what forms the precipitate. So the net ionic equation is this. And the spectator ions are the sodium ion and the nitrate ion. So that's the whole process. We have a couple more examples of this, so this is definitely a time to hit pause, then go ahead and try this on your own and see how you do. Now cross off the spectator ions and write the net ionic equation. And double check and make sure that it should still be balanced, okay? And make sure, especially in this case, that your oxygens and your lowercase o's are significantly different sizes. Okay, here's another one for you to try. I'm just going to write down the answer, and if you have some difficulty, we can go over it tomorrow. This one again, another one to try, and this time you need to translate these word equations into a balanced chemical equation first. This one I'm going to leave completely blank, and I'm going to check to see, so I will check this, to see that you have completed this tomorrow. So try this one the best you can. But now we're going to move on to the other two types of reactions. This is the reaction that forms water. So that's an acid-base neutralization reaction. We haven't really talked much about what acids and bases are, and we won't really until the very end of the course. But you may know from middle school that an acid is a compound that it generally begins with an H plus or an H. HCl, HBr, HI, H2SO4, HNO3. A base generally ends in OH minus, NaOH, KOH, CaOH2. When those two mix together, as you can see from this reaction down here, the OH from the base and the hydrogen from the acid come together to form water molecules. Water molecules, right, have a neutral pH. And so the acid and the base, when they come together, they neutralize. That's why this compound, milk of magnesia, which is just magnesium hydroxide, is good if you have an upset stomach. If you have an upset stomach, sometimes it means you have too much acid. And then you drink the milk of magnesia, and the base in the milk of magnesia and your stomach acid neutralize and just form water. So in a solution, if there's H plus and OH minus ions present, those will react to form water. There's different types of acids. In this case, we're looking at the most simplest form. You don't need to know this. They're called Arrhenius acids. So Arrhenius acids and bases placed in solution together, the hydrogen ions and the hydroxide ions react to form water molecules. The example is sodium hydroxide, which is a very common base, and hydrochloric acid. And so you can see we write them, dissociated, and then the positive sodium and the negative chlorine would form water or in ionic compounds, depending on what they are. But you'll always have, because an acid is always H plus and a base is always OH minus, you'll always have H and OH coming together to form water. The other compound that's formed in this case is NaCl. NaCl is soluble in water, so they are spectator ions. So therefore, if I write the complete ionic equation for this, we can notice that Na plus and Cl minus are the same from beginning to end. Those are spectator ions. We get to cross them off. And the net ionic equation for all acid-base neutralization reactions is essentially the same. If we don't know this yet, if they're strong acids and strong bases, it's just H plus OH minus yields water. And these are called neutralization reactions because you will make a neutral compound. Neutral pH is 7, acids are less than 7, and bases are greater than 7. So it sort of makes sense that if you add something that's less than 7 and something that's greater than 7, if you mix them in exactly the right quantity, you'll get exactly a 7 pH. So here's an example here, phosphorus acid plus potassium hydroxide. So H3PO3, all acids are aqueous. Potassium hydroxide, KOH, and you can look on the solubility rules, that is also aqueous. What is that going to form? Positive of one, negative of the other is going to be HOH, that's water, and that's liquid, that's not aqueous. And then the other product that forms is K3PO3, and that is aqueous. So that's the chemical equation. To balance it, I would put a 3 there and a 3 there. Now it's balanced. If we go through and write the complete ionic and the net ionic, I'm going to notice that after I get that written down, I can notice that this is the phosphite ion, is a spectator ion, and the potassium ion is also a spectator ion. So what is actually reacting? What's the net ionic equation? As we said before, the net ionic equation for acid-base neutralization reactions is almost always just H plus OH minus makes liquid water. I could reduce those down to just 1, 1, and 1. And then the last type of reaction is reactions that form carbon dioxide or a gas. Carbon dioxide is the only example we look for. This happens only under very specific circumstances. You have an acid and then an ionic compound containing hydrogen carbonate, because when acids with an H and hydrogen carbonate combine, they make H2CO3, which is called carbonic acid. This immediately decomposes into H2O and CO2. That's your gas and your liquid. That's how you have a reaction that forms, that it isn't a precipitate, but it's still a double replacement reaction. The most common example of this is vinegar and baking soda. So if you think about what vinegar is, and you probably don't know this, but vinegar is acetic acid, CH3COOH. I know we said acids usually begin with hydrogen. Usually, this is an example of one that doesn't. And then baking soda is NaHCO3. And we would be adding that as a solid, right? And you guys have probably done this where you've added baking soda and vinegar together and it makes all sorts of bubbles, right? This is like the classic middle school volcano experiment. So we're going to do the same thing that we always do here, right? Positive of one, which is going to be the hydrogen, weird, and negative of the other. That's going to be our H2CO3. This is the one that we said you have to keep an eye out for because that's going to decompose. And the other product is sodium acetate. That's aqueous, and that's where my spectator ions are going to be. And then this guy immediately decomposes into H2O liquid and CO2 gas. So if I were to write the whole equation out, I would have CH3COOH aqueous plus NaHCO3 solid. I'm not splitting up the vinegar, acetic acid, because it's a weak acid. Again, I'm not going to test you on that. Sodium hydrogen carbonate is a solid. These guys will form the liquid, and then these are the sodium is aqueous and the acetate is also aqueous. Okay, and this just shows you down here a graphic of what this would look like of the vinegar and the baking soda, and you mix them together and you actually get the carbon dioxide as a product, because remember that H2CO3 quickly decomposes into carbon dioxide and water.